Okay, in this lecture we're going to talk about how to mathematically model a DC motor. So if we're going to be designing a control system to work with this motor and driver, we need to understand mathematically what that system response and or transfer function looks like. So we're going to talk about the DC motor and driver, and we'll look at coming up with a suitable mathematical model for that. Okay, so for your final project, you'll be implementing a control system in the microcontroller that will allow a simulated DC motor to reach a commanded RPM value in a quick and stable manner with minimal overshoot. So since we don't really have a lab, or it's kind of hard to deal with actual hardware, we're going to actually simulate the transfer function of a motor and driver in the microcontroller and then wrap a control system around that. So we'll have one overall transfer function that will represent the controller and the controlled system. And then we can design that controller such that we get the performance that we desire, correct or suitable performance parameters out of that combined system. Okay, so this will be based on actual real data. So I'll be giving you some data that you can use to develop this model. It is based on measured data. So what we're using is this DC motor and wheel that you see down here on the left. Something you can buy on Amazon for it's a few bucks. It's not that much. And this L298N DC motor driver. So if you're interested in getting more information on controlling these, I can give you some more information, but essentially this driver accepts a PWM signal, and it creates a driver voltage for this motor that will make this thing spin at an RPM that is roughly proportional to that drive voltage. It also has a encoder here on the back, this little black piece sticking out. That is a rotary encoder that is sending A and B channel pulses out, so we can use the microcontroller to basically interpret those signals using encoder mode, and we can measure the RPM, so that kind of provides the feedback. So when we're simulating this, that'll be obviously more mathematical thing, but you can actually do this in hardware where you design only the control system in the microcontroller, and the measurement of the rotation is actually done physically with this encoder. Okay, so for the actual hardware system, this is kind of what that looks like. This dashed line here is the microcontroller board. We have our console here outside where we're looking at maybe a USART stream, which is going to contain our RPM values that we're sensing. That's what I'm going to record and give to you as data, and then you're going to build your model so that a step response in your model matches what we actually measure for this system. Okay, so up here we'll have our motor and our driver, and this is the transfer function we're really going to need to try to come up with in this lecture, right? Okay, so that's driven by a timer PWM percent duty cycle. So you can think of that as being driven by a value between 0 and 1, right? A duty cycle between 0 and 1, or between 0 and 100%. This is our actual controller, so it's going to take the RPM error and generate that duty cycle. So that's done mathematically, right? So this is our control system that we've implemented in the microcontroller. Could be a PID controller or any other type of controller that you want to develop. Okay, then this is the physical motor. So this is the Y of S is the actual RPMs. Okay, so RPMs can then be sensed. So this H of S is our feedback loop, and it consists of the encoder, which is interpreting actual physical RPMs to encoder pulses, and then we're using a timer in encoder mode and some calculations to generate a measured RPM value from that. So if you look at it, we've kind of set this up to where this H of S block really has a transfer function of 1, right? It's RPM in and it's RPM out. So it's a physical RPM to a calculated or estimated RPM. But essentially that's going to have a transfer function of 1. So that gives us that unity feedback that we're looking for, which makes the math and the overall transfer function a little bit easier, right? So it's always good to write the code so that that h of s feedback block has a transfer function of 1. So you want your calculations, your sensor and your calculations, whatever you have to do to make this equal calculated RPM equal, whatever this physical parameter is out here you're measuring. Okay. So we need to characterize these transfer functions so that we can design this D of S controller. Okay, system identification. This is a topic that's pretty popular with systems. MATLAB has a lot of tools for coming up with the model for a particular system, but a lot of times you want to come up with a mathematical description of a physical system. That's important, so you can simulate it. You can use that model to combine with your controller transfer function to get an overall closed loop transfer function, and that is what you're going to look at the performance of. Okay, so in order to design a control system with suitable transient response to step commands, we need to understand the entire transfer function, which means understanding the entire chain. So really it's good if we can break this down into pieces. So if we start with the motor and driver, we have a motor with an angular velocity, so we're calling that theta dot. That's really what we're considering our output, and that is what we're measuring. That's given a drive current from the driver that's based on the input PWM duty cycle, which is generated by timer 2, which is generating a duty cycle per pulse value. So when we put in a pulse value in the code, that's going to vary between 1 and 10,000. So we must be using an ARR of 10,000, so that pulse value can vary. So duty cycle per pulse value is 1 over 10,000. That pulse value is then determined from our RPM command, and we have some pulse value, per RPM conversion there. So, that's just basically saying we know that an RPM of 100% is going to give us some velocity if you count for all these things in the chain. So a lot of this stuff we don't really care what the specifics are. We don't really care what the specific drive current of the motor is. We don't really care what percent duty cycle specifically causes it to turn at a certain RPM. What we really want is for us to put in an RPM command here and have the motor give us, that specific RPM that we commanded. Okay, so this is kind of the open loop chain of conversions. We don't really care about a lot of this stuff in the interim. So if we make a measurement, say we set an RPM of 100%, measure that angular velocity, then we can kind of use that to model this section of the motor. Okay, so we really just want to find a transfer function that gives us PWM duty cycle to motor angular velocity. That's really what's going to be in our G of S, our motor and driver transfer function. Okay, so this will be, you can consider this like a step input, right? If we were to do a 0 to 1, and that's going to give us some sort of response on our angular velocity. Okay. Okay, so for the motor and driver, we need a dynamic model for this motor to determine the transfer function. If we can command a step of 100%, like from 0 to 100% duty cycle, and record the transient response of the system, record the RPMs over time, then we can try to find model parameters that match that response. If you look at the dynamic equations for a DC motor, those are given below, and you can see they're kind of complicated, right? So we have the back EMF is equal to the resistance in the motor coils times the drive current, plus this back EMF constant times the theta dot, right? The velocity. Okay, so that's one equation. And we also have torque is equal to the torque constant times the drive current, and that's equal to this inertia of the rotor and the wheel attached to the motor times the acceleration, angular acceleration. Okay. All right. So that those are the kind of the governing equations for the DC motor. But you can see, you know, a lot of these we don't really care about. We don't really care what specifically the resistance of the motor coils are, what the drive current is. So what we're going to do is we're going to come up with a kind of an equivalent transfer function that uses all these parameters. And you'll see that we can combine a lot of these parameters and just condense those into one constant. Rather than having to know specifically what RA is and KB and KT and JA, we'll be able to come up with a combined constant that kind of represents all of those. Okay, so if we take the Laplace transform of these two equations, we get this. So the voltage is equal to RAIA of S plus KBS times theta of S. Okay. All right. And KTIA of S is equal to JA F squared theta of S. So that's the Laplace. We can combine these to find the output, this theta of S for an input voltage. So this gives us theta, which is position of the motor per voltage, is equal to this response. So this second order response, right? Okay, so here you can see we're starting to combine a lot of those constants, and that's where we don't really need to know specifically what these are. These are, you know, these are related to physical properties of the motor, but since we're going to be matching this transfer function to a measured response, we don't necessarily need to know how all of these individual parameters are distributed. We're just looking for, you know, parameters of this entire transfer function. Okay, so really we can define a new constant, T sub m, which is going to be these four parameters, right? RA, JA over KT, KB. We don't really need to know individually what those are. We just want to know what the coefficient here is for S. So we're going to define a new constant. And since we're interested in the motor speed, which is the derivative of position, we can write the transfer function in terms of angular velocity. So instead of theta sub S, which is position, we're going to multiply that by S. Okay, that's going to give us basically theta dot. So the angular, we're going to call that angular velocity. So the angular velocity with respect to voltage now simplifies to just this first order transfer function. Okay, so what that means is the RPMs, the angular velocity is just going to be a first order exponential curve, right, for a step voltage input, or for a specific voltage, right? Okay. So now we need to account for the motor driver, which we're going to model just as a simple conversion from PWM duty cycle P percent P to a drive voltage. Okay, so we're basically going to say the drive voltage out of the driver is going to be some constant, you know, times P. So here we don't really care what drive voltage represents what duty cycle, but we're just going to model that together basically. Okay. So with all that, we arrive at the transfer function for the driver and the motor. So this is angular velocity per 100% duty cycle. Okay, and then this becomes KD over KB over TMS plus 1. And then here we're going to combine KD over KB into one constant we'll call KG. Since we really don't care, like I said, about how exactly drive current, we don't need to know how many amps per duty cycle. All we really want to know is how fast the motor turns with a certain PWM input, right? Okay, so if this is 1 or 100%, you know, then we're basically saying this angular velocity is going to be this transfer function with a step input, if that makes sense. Okay, so we've kind of boiled it down into just two parameters, and that's combining the parameters of the driver, this driver constant, and the four constants that go into this T sub m and this KB. So all of those constants kind of boil down to really two unknowns that we need to find, two coefficients in this transfer function that we need to determine. That's going to really drive what this response looks like. Okay, so we're calling this G sub S, which is going to be RPMs per PWM input, which is going to be kg over TMS plus 1. So that'll be our motor and driver combined transfer function. So the input would be a PWM duty cycle between 0 and 1, and the output would be the angular rate of the motor. Okay, so if we want to find the response of the system to a step in PWM input, we can, oh, and here we've just kind of done some, we want to get the coefficient of S to be 1, so we've divided the numerator and denominator by T sub m, so we get this kg over Tm is S plus 1 over Tm. Okay, so if we want to find the step response to a step in PWM input, we can basically multiply this transfer function by the step input, which is 1 over S. And we're basically saying this is going to be a step from 0% duty cycle to 100% duty cycle. So a step from 0 to 1, that's our typical unit step function, right? Okay, so y is equal to g times u. U is our step function. So then we get y of s is equal to that combined transfer function. And then we can do partial fraction expansion to find these coefficients r1 and r2 before we take the inverse Laplace. So we can do partial fraction expansion. If we do that, we can do a little bit of algebra. And we basically have where, you know, the coefficient of s in the numerator is r1 plus r2. You can see in the numerator there is no coefficient of s, so r1 will be negative r2. Also, we have coefficient, the constant coefficient here is kg over Tm, which over here is r1 over Tm. So that tells us that r1 is going to be equal to kg. Since r1 equals negative r2, we know that r2 will be equal to negative kg. So just one possible way to do partial fraction expansion on that second order transfer function. So if we write that out up here, we've got kg over s plus negative kg over s plus 1 over Tm. And we can do the inverse Laplace transform of this, and we get y of t equals kg minus, and then here's a minus kg e to the minus t over Tm. So this is something we would expect to see, right, for a first order transfer function, a first order step response. We'd expect this to be, you know, some sort of an exponential. So that's what we have. Okay, so our motor and driver will have a step response, and here I'm saying omega of t. You could say theta dot of t if you want here. That's probably a little bit more correct. But here we're basically saying the speed of the motor is going to be this kg constant times 1 minus e to the minus t over Tm. Okay, so what I did was I wrote a microcontroller application that applied a step voltage, and then I used the USART to record out that motor RPM over time. And of course, you know, it's not a very clean signal. It's kind of a weird, there's some noise in it, some oscillations, but you kind of get the gist of the exponential nature of it when you see it. But basically we can use that exponential, we can plot that like in Excel, and then we can basically find kg and Tm values that will produce this response that matches it, really. So it's kind of a, that's why they call it a model identification. In this case, it's just two parameters, and one of these is very easy to determine, and the other one is kind of derived from that. So it's pretty simple, but you can imagine if you have, you know, 20 parameters, it may not be as simple as just, you know, tweaking these till you get it right. So there are some other techniques for more complicated models, but for us, this is going to be pretty simple. So once we have these values, then we know our G of S. Our G of S is simply this right here, right? Kg over TMS plus 1. Okay. All right, so we want to form this mathematical model. I'm going to provide actual RPM output for a DC motor step response. And I think the best way to do it is to load this into Excel. So one column might be time, the next column will be this data that I'm going to provide you, and the third column can be your mathematical model, which is this step response, right? So this is the step response you'd expect to have. And then you can kind of tweak these two parameters in Excel and till those curves kind of overlay each other and match. So this is a real simple way of basically determining what these parameters are. Okay, so this is kind of what it'll look like. So the blue line is the actual measured RPM of the motor. So you'll see it's got some oscillation kind of on top of it. I'm not sure exactly what that is, but I think that was that it was kind of right on the edge, so it was kind of toggling between values in that RPM response. It was toggling, you know, between maybe 181 and 182 or 3 or something like that. Of course, this is kind of a smooth Excel version of that output, but you know, I think it's good to kind of try to just split that in the middle. And you know, so I put that in Excel, that data, and then I also created this response in Excel, and I just pretty much tweaked KG and TM until the curves I thought looked about the same. So you know, TM is going to be your time constant. So with TM, you know, raising or lowering TM is going to make this response, you know, much slower or much faster. So you can adjust that, and then this KG is going to be kind of your final value, right? So at t equals infinity, then this output will finally be TG. So it's pretty easy to find TG just by looking at this. So by tweaking KG and TM, it's pretty easy to find two parameters that give you a really good, reasonably close match between these two. Okay, so that's really what the next assignment's going to be, and we'll call it the model identification assignment or something like that. And basically, that's the assignment, is to, you know, take that data that I'm going to give you and mathematically determine what KG and TM should be. And then I want you to basically show me your plots. I want to see you plot the data that we read and the data of the, you know, mathematically equivalent transient response for the parameters that you came up with. I want to see how closely they match. Okay, so that assignment will be providing the two values, KG and TM, as well as you know, a plot of both on the same axis, so I can see, you know, how well this match. Okay, so once we have this, KG and TM, then we'll have our mathematical description of the motor and driver, and that's what we can use as our controlled system in our controller design, right? So if we want to design a PID controller, then we can you know, use that G of S in our overall closed loop transfer function to get the type of parameters that we want. Okay, so look for that assignment, and look forward to seeing the results. And once we have that model, we can move on and start working on the final project. Okay.